product and quotient rule. That's kind of where we are. Here's a product rule. Pretty straightforward one. Call this guy F, call this guy G, and then you use the product rule. In this case, F dash Z, the derivative is F dash G plus F of G dashed. If you differentiate 4, take away e to the Z, you get negative e to the Z. And then you leave that second one alone, so you get that. And then you add, we'll leave the first guy, this guy alone. And then be careful, when you differentiate this, you don't just get e to the Z, you get 4 plus e to the Z. And that's pretty much the calculus finished, but not the question. From this point onwards, our job is style points. So what I'm going to do is I'm going to distribute that. I'm going to FOIL that and see what we can get out of it and see if we can tidy it up even. Right, you multiply this guy by this and you get negative 4z e to the Z. This guy times this guy. Okay, let's show you a little algebra that some people get wrong. If you multiply e to the Z by another e to the Z, the answer is obviously negative and it's a power of e. But it's not e to the Z squared. What do you get if you multiply e to the Z times e to the Z? What's the power of e that you get from that?
E to the 2Z.
Right. So bear that in mind. When you multiply things together, you add their powers. So back to this one, you get negative e to the 2Z. This guy here is going by FOIL, so that's 16 plus 4e to the Z, take away 4e to the Z, and that guy times that guy gets you negative e to 2Z again. Anything interesting going on? Well, those two guys here and here cancel each other out. Those two can get joined together and that one's on its own. So it's negative 4z e to the Z. Take away 2e to the 2z and plus, it's like a 16. I don't think I can, I'm just thinking, I don't think I can do anything particularly, beneficial. So I'm going to call that one good. I mean, I should try and pick out a common factor. Technically, 2 is a common factor, but would you agree taking out 2 is not really going to make much difference to that question? So in that case, I don't think it's worth bothering. Now, the next one I'm picking is for style point reasons. In particular, some algebra that you're probably not comfortable with or have seen often. So the question is going to start off relatively straightforward. Which is this guy here. We're going to do a product rule. Again, nothing too surprising. Call that F, call that G. In order to be able to differentiate it, I'm going to rewrite the square root as a half power. So I should be able to start the derivative. Product rule, F dash G plus F G dashed. If you differentiate this guy, you get 1/2 x to the negative 1/2 times, leave this guy alone. Leave the first guy alone, just x to the half, and differentiate by this guy, and you get e to the x. Let's do some style points. You can certainly pull out e to the x. Both of them have it. And this fella here is now going to be called 1 over 2x to the half. And this guy here, for the time being, is going to be called x to the half. And you might think, nothing wrong with it. In a lot of ways, there is nothing wrong with it, but it's not the best it can be. There is another common factor that you can pull out. And so you have to go back to here and look at this in a different way. And it's not a normal common factor that you would be typically used to. But it does happen enough times that we have to kind of dwell on it and show you what you do. E to the x is a common factor. No arguing about that, it truly is. I have here an x to the half. I have here an x to the negative half. If both terms contain a power of x, no matter how weird that power of x is, in this case it's a half and negative half, then x is a common factor. And now we have to decide, is it x squared or x to the half or x cubed, right? What's the common factor? Now, when you have two choices, one is negative a half and the other is plus a half, or whatever the two choices are, your common factor is the smaller of the two. So these two terms share a common factor of x to the negative a half. Right? I'm not sure if you've ever seen that trick with that common factor process where you can do it with fractional, in this case, negative fractional powers. So x to the negative a half. Now, this guy is all that's left. If you use up that and you use up that, fair enough. E to the x used up. Now the tricky part, and we're finished. This guy is x to the half. What happens if you suck out x to the negative a half? So you've got x to the half and you remove a negative a half from it. What do you get as a power of x? So you've got x to the 1, and you're going to remove from it negative a half power. Any takers? What power of x goes here?
One
X
half.
to 0.
Well, I can understand why you think it would be half, but it's 3 halves. So let's try and argue it. Oh, sorry. X to the 1. Right, let's try and argue it. Half a power remove, and I don't know why it's did that. Half a power remove negative a half is half a power add a half. You get x to the 1. So this guy is e to the x. This guy is a half plus x. And this guy can now go in the bottom. And you are pretty much finished. And that is the first derivative. Now this question then gets you to do a second derivative, but I'm not going to talk about them, this particular one, because to get the second derivative, you have to take your answer, which would be probably this one, because it's the easiest to work with, and differentiate it. So essentially you have to do 2 product rules. But that's a really long question, and we don't have time. So let's now look at quotient rule. You use the quotient rule when the function you're trying to differentiate is a fraction, right? It's got an expression of x on the top or a number and the same thing on the bottom. So an example of that would be question 14. rewrite that again. There we go. Now, the top function, in this case, e to the x, is called f. The bottom function, in this case, 3 minus e to the x, is called j. And the quotient rule is this one over here. And it says that the derivative is f dash j, take away f of g dashed, all over j squared. This is a lot more working than a product rule. So you differentiate the top and you get e to the x, then you leave the bottom alone. Take away, you leave the top alone and you differentiate the bottom. Well, 3 take away e to the x is just negative e to the x. And then on the bottom, the denominator, you put the value of j and you square it. So for finish the derivatives, this bottom term squared is almost never altered. Just leave it the way it is, right? On the other hand, the top expression has a lot of things that need to be done to it for style point reasons, right? Foil it out, collect like terms, or if you notice, as I have here, that there's already a common factor I can use. If I pull out a common factor, I'm left with 3 minus e to the x minus this guy, which is a plus e to the x. So the bottom remains untouched. These two cancel and you get 3. Now, if you don't like the idea of pulling out e to the x as a common factor and removing the rest, couldn't you just distribute these and combine like terms? You'd still get 3 e to the x over that guy squared. And that's finished. Nothing else to do. Okay, any questions? Been going on for a while. Okay, let's continue.
I had a question. So
Yes.
in the beginning, like you couldn't cancel out the 3 minus e to the x with the bottom 3 minus e to the x.
Correct. So let's have a look at that. Here. Oh, okay. So you're not allowed to cancel this guy with that guy. This is correct. And the reason you're not allowed to cancel is that the top guy has to be a factor of everything. It can't just be, it belongs to one piece and the other piece doesn't have it. You're not allowed to do that. A simpler example of that thing not being allowed is, can you imagine you might have 5x squared plus 1 over x cubed, just for argument's sake. You are not allowed to do one of these and say 5 plus 1 over x squared and get me 6 over x squared, right? It doesn't work. Right? You see how this one's got it, but that one doesn't. That's kind of the same reason, just a little bit uglier. So you can only cancel things on the top and the bottom when the top is completely factored and one of the factors happens to be the guy in the bottom. That was a good question. Okay. Let's do a polynomial on the top and a polynomial on the bottom. So let's suppose I have a function x squared minus 3x on the top and x squared plus x plus 1 on the bottom. And I want to differentiate it. Top guy's f, bottom guy's g. So f dash g, take f of g dashed over g squared. Okay, you differentiate the top, you get 2x take away 3, and you leave the bottom alone. Minus, leave the top alone, and differentiate the bottom with respect to x. And then finish with whatever is on the bottom squared. And that's pretty much calculus finished with. So I'm going to have to make this look pretty. So if you just left it like that, you'd be, well, I'm pretty sure Web of Sign will say you're wrong. But even if it says you're right and gives you points, you're wrong. These need to be done as simple looking as they can, right? You must do style points, which means that these questions do grow. They become extremely big before even anything nice happens. So I'm going to do 2x times this guy, 2x cubed, 2x times that guy is 2x squared, and 2x times him is 2x. Then I move on to the -3. -3 times that guy, -3 times the middle guy, and -3 times the end guy. Then I'm going to put a minus and FOIL these out. And that gets me 2x cubed and x squared, a minus 6x squared, and a minus 3x. All of the bottom squared. Now you're looking at that, you should be saying, God, that's ugly. I agree it is. And it probably won't get much better, but sometimes you're pleasantly surprised. So I can try and collect some terms here while we're at it. That's 2x cubed. 2, take away that is minus x squared. 2, take away that is minus x. There's a little bit of tidying up. That guy's on his own, so you'll take him away. And that guy gets you minus 5x, but when you take it away, you get 5x squared, and you get an odd 3x. And let's see. Can you see anybody collecting like terms? Can you see anybody getting killed off in the top?
X cubed.
Okay, those guys gone. Apart from that, I think it's just a matter of collecting terms. So 5x squared take away 1 leaves me with 4x squared. Plus 3x with a minus x leaves me with plus 2x. Take away 3. And I have one quick look. And I see if I can factor that. And I can't. So we're finished. So you're going to be spending a lot of time on these questions, foiling, factoring, collecting like terms, those types of things. And they are quite time consuming. Let's do a fraction function, but a little bit different. There's going to be a 1 on the top line. So the top function is going to be f, and the bottom function is going to be g. And the derivative is going to be f dash g, take away f of g dashed over g squared. Quotient rule. Right. What makes this a little different? There's a number on the top instead of an expression using x's. What is the derivative of 1?
0.
So what you're going to get is 0 times this guy. Take away 1 times the derivative of this guy, which is what? 18x squared minus 4x. And on the bottom, you basically just get this guy squared. And here's the cool thing. Isn't 0 times this guy just 0? So I don't even need to do the details. I know it's their whole lot's going to be 0. Minus 1 times this guy is negative 18x squared plus 4x. So we're in making it look pretty stage now, style points. Pretty nice looking, but I can do better. On the top, the numerator, typically it's always going to be there that we look. Is there anything I can do on the top?
You could pull up a 2x.
That's what I would do. And that would leave me with what? Negative 9x plus 2, which is what it is. And then I can just rewrite the bottom. And let's see if I've done the style points rules. Does it look like the original? Yeah, it's a fraction with polynomials in it. Is it factored the heck out of it? Yep, I factored everything I could factor and I'm done. The next one I'm going to show you is scarily ugly. And it's going to be question 18. Square root of x, square root of x plus 3. Quotient rule, pretty obvious, it's a fraction, so it's a quotient rule. Well, I won't really differentiate these guys because these guys aren't really designed to be differentiated. So I'm just going to rewrite it like that, okay? So if you differentiate the top, you get 1/2 x to the negative 1/2, and then you leave the bottom alone. Minus, leave the top alone, and differentiate the bottom, which gets me that guy all over the bottom squared. Right, I think it's living up to its expectations. Would you agree that is really ugly looking? So now we have to make it look prettier. So first thing I'm going to do is distribute. So I'm going to do that guy times that guy. I'll do this at the side. Something quite strange happens. If you take 1/2 x to the negative 1/2 and you multiply it by x to the positive 1/2, what do you get? Well, normally when you multiply powers of x, don't you add them, right? So negative 1/2 add 1/2, right? But isn't negative 1/2 add 1/2 0? So you would get x to 0. But what is that?
Just 1/2.
Just 1/2. So a little bit weird that, isn't it? That you actually multiply some ugly powers of x together, but the net effect is you just end up with 1/2. Now the next one is equally ugly, but nothing really weird happening. And this one times this one does that half thing that I talked about, right? This time with a negative. And now we're looking at this answer. And you might think, well, you can't factor it. There isn't any more foiling worth doing. I guess I'm finished. But you're not. What have I still to do?
Make it look like the original.
Right. And how about that negative 1/2 while I'm at it? What should I do about that?
Bring it to the bottom.
Okay. So I'll put it down here. And I'm putting in more lines than you would ever want to. Okay, so that's down there. And just like you say, make it look like the original. And what about the 3/2? Should I put 3/2 on the top, or could I write it a little bit nicer than that? What about that too? Leave it on the top or bring it downstairs? What about that too? Looks nicer down there, doesn't it? A little bit cleaner. Right, now make it look like original. All in all, wasn't that an ugly question? Right. Didn't have a nice look to it. It came out okay, but not the prettiest question in the world. Any questions again? Are we good with that? I've mentioned this before. I don't think people know that when they sign up for Calc 1, in a lot of ways, aren't you signing up for algebra class? Because a lot of what we're doing is algebra. Now, question 19. Chose this one, not because the question is difficult, because I don't think it is. It's because of what's on the bottom. When you write a function in this format, that R is telling me that R is the variable. What it's also telling me is that any other letter of the alphabet that appears, like A and B here, they are just constants. That means they're a number, right? They're 4 or 42. And don't really know what number they are, but we know they're a number. So treat B and A like they were 5 and 4. So the top is F, bottom is G. It's definitely going to be the quotient rule. Differentiate the top, you get e to the r, leave the bottom alone. Take away, leave the top alone, and then multiply by the derivative of the bottom. So this says b plus a e to the r. With respect to the variable r, what is the derivative of b plus a e to the r? Any volunteers? What is the derivative of this? If you think of that as 5 and this is 4, what do you get when you differentiate?
A e to the r.
Correct. Isn't that like a 5? Well, 5s when you differentiate them become 0. Isn't that like 4e to the r? And when you differentiate 4e to the r, don't you get 4e to the r, right? So A is just like a 4. You got that. Now at this point here, we should be getting a little bit more familiar with what's required of us. We have to make this look pretty. So first thing I'm going to do is distribute. Then I'm going to collect like terms. And then maybe not, I'll get some cancelling. So if you distribute this guy, and you multiply this guy by this guy, you get A, E, and then E to the R times itself gets you 2R. And you multiply these together, and something really nice happens. You get that. Those cancel out. And you now are left with essentially the answer. We're done. Any questions? What I'm trying to do today, and definitely yesterday, is do as many different variations and things, as many different product rule situations and quotient rule situations as you can, so you get practice at the algebra of making them look pretty, which is a big thing, obviously, and get practice at just doing a product or a quotient rule. We have, I'm looking through here. Yeah, I guess I need to do this one because I don't think we've quite done one like this. We've done a lot of square roots. We haven't done that many cube roots yet. So here's another quotient rule. Since I know I'm going to be differentiating, are you comfortable with the cube root being rewritten as a 1/3 power? Square roots get you half, cube roots get you a third. Now we can move on to the derivative quotient rule. Okay, if you differentiate the top, you get 1/3 t to the -2/3, right? Multiply by the power and reduce it by 1. Leave the second guy alone. Take away, leave the top guy alone, that's him, and differentiate the bottom, which is actually just 1. And all over the bottom squared. So I'm now going to multiply this guy and this guy together, and that will get me 1/3. Well, a -2/3 and a 1 combine to give you +1/3. And then this guy times this guy gets you negative, oh, the thirds cancel. So it's a little bit nice. And then you get this guy. This guy and this guy kind of sort of a combine. You've got a 1/3 take away 1, so you get -2/3. And you're now looking at that. The numerator both contain powers of t. T to the -2/3, t to the +1/3. You see that? -2/3, 1/3. That means whenever that happens, then some power of t is going to be a common factor. Is it t to the -2/3 or is it going to be t to the third? The rule is when you have a choice, pick the smaller of the two. So it's -2/3. Now, if you use this as a common factor on this guy, you get -1. And this guy, you're going to get -2/3. And now the tricky part. You've got 1/3 and you're going to take away -2/3, right? So you've got 1/3 power and you're going to take away -2/3, which really means 1/3 add 2/3, which is in fact 1. So you get t to the power of 1. And if you're not convinced that that's true, distribute that, you'll get back to here. And style points has got a little bit more to go, but we're pretty much done the hardest part. That negative is going to come downstairs. Then I'm going to make it look like the original. That guy is a cube root of t squared. So there's your really ugly looking answer. Taking a different tack for the next one. There's a rule that I call just because you can doesn't mean you should rule. This question could be done by using the two terms the way they're written and doing the quotient rule. And eventually you would get the correct answer. You probably wouldn't like the working, and you certainly wouldn't like the style points. It's really ugly. So just because you can doesn't mean you should roll. It's basically a catch-all phrase that I use for sometimes you can do a question different than the obvious way. So I am going to multiply the top and bottom here by x. Right? It's a special version of 1, so I'm allowed to do that. So I get x squared. X times that is x squared plus cx. So this new version of f of x is this one. Would you agree that that is actually quite easy to do? Right? It's going to be nice, relatively. And so that's the guy that I'm going to use a quotient rule on. Not necessarily the guy they give you. If you can make it look different and make your life easier, you should. So it's f dash g, take away f of g dashed over g squared. Right, differentiate the top, you get 2x, leave the bottom alone. Take away, leave the top alone, and differentiate the bottom with respect to x. So that gets you 2x, and cx just gets you a c. All over the bottom guy. Squared. Distribute 2x cubed, 2cx squared, take away 2x cubed, take away a cx squared. That guy cancels out that guy. 2 of these take away 1 of these, leaves a single cx squared. Oh, isn't that nice? Come on, that is a nice question. Trust me, if you try to do it like this, you would definitely not like the road that you end up traveling.
I have a question on that one, actually.
Go for it.
Oh, I can't see it anymore.
I'll bring it back. There you go.
Oh, yeah, there you go. So in the beginning, when you turned x plus 6 over x, it turned x squared plus, or c. It turned to cx. Wouldn't it just be x squared plus c?
Ooh. You are right.
I can't change the whole problem.
It does a little. It makes that a c, makes that a c, makes that a c. And it reduces this by 1 power. But everything else cancels out. So you're right. Very similar question. Ends up being very nice as well. So moral of that story is I make mistakes, not in the method, just being careless. If you see that, shout earlier. It'll make things work. I'm looking at some stuff here to see what we haven't covered. Now we've done square roots. Okay, I think it's time for us to do multiple derivatives. So what I mean by that is not just finding f of x, but finding second derivatives as well. So you find that they have questions where you find the first derivative and then they go and they say, well, now you found the first one and find the second. So here's my first example. Suppose you had x squared e to the x. It's a product rule. Make that f, make that g. And its derivative, according to the product rule, you get by doing that. You differentiate this guy, you get 2x. Leave this guy alone, you get x squared e to the x. And then if you want to make it pretty, what are the common factors you could do with this question? What kind of common factors can you pull out of this?
E times e to the x.
I think you probably mean x times e to the x.
Oh, yeah, I don't know why I said that.
I got the gist of it. There we go. And that's the first derivative done. Now you come to find the second derivative, which basically means find the derivative of this guy. Now there are two different approaches to this question. I'm going to call this equation 1. I'm going to call this result here 2. If you start with 1, can't you find the derivative of this with the product rule and the derivative of this with a different, right? It's essentially two separated product rules, right? So you do the product rule on that and get your answer. You do the product rule on this, get the answer, and then combine everything. And that will work. Or you can try method 2. So let me show you method 2. Some people like this trick, other people don't. This function is essentially made up of 3 things multiplied together, right? An x, that's the first thing. An e to the x is the second thing. And this 2 plus x is the third thing. I'll have to take a little bit of room here. We know the rule for the product rule. Here it is here. Do you know that you can expand the product rule for 3 things multiplied, right? So the product rule is now going to contain f, g, and h. Does anybody want to have a shot at what the product rule would look like for 3 things, rather than just 2, which is this? And it's not a weird formula. It has a lot of symmetry, a lot of similarity.
Is it f dash times g times h plus f times g dash times h times f times g times h dashed?
Doesn't that seem very symmetric? And it is. That's the product rule for 3 things being multiplied. Now you could expand it to 4 or 5 things, but nobody ever asks you to differentiate 4 things that are all multiplied. So I wouldn't worry about it. But you could get some 3s, which we have. So let's see what that looks like. That guy is 1. Leave the other 2 alone. Leave the first one alone. Differentiate the second one. Leave the third one alone. Leave the first one alone, leave the second one alone, and differentiate h, which just gets you 1. And now we're into essentially style points here. If you multiply this out, and this guy. And then I can collect its like terms. I guess I should. I've got this guy. Got this guy. Got this guy. So what's up? Okay. I hope I got those all right. What do we do next to make it look even prettier? I've got this expression. What could I do to finish the question off?
Take n e to the x.
Okay. Now, I'm going to rewrite it in a slightly different order because I think x squared belong first. I should look at this quadratic just in case you can factor it. And if I could factor it, I would. But this one you can't, so we're finished. So first derivative, second derivative. Do we have time? No. Okay. Then I'll make up a simpler one that we can do. A very simple quotient rule where we're going to find first and second derivative. So I've chosen a very easy one because we only have so much time left. So f dash g, take away f of g dashed all over g squared. If you differentiate the top, you get 1, leave the bottom alone. Take away, leave the top, differentiate the bottom, all over x plus 1 squared. And this guy here is x plus 1, take away an x, over x plus 1 squared. And the x's cancel. And there is our first derivative. Agreed? Now, second derivative. Style points, you would leave things like that. But if I want to differentiate this, which I do, I'm going to have to rewrite it like that, right? I'm going to have to turn that x plus 1 squared into what it would equal when you FOIL it. So the top is going to be called f, the bottom is going to be called g. And we'll do the quotient rule all over again, but with new guys. So what do we got? The derivative of 1 is 0 times that guy. Take away 1 times the derivative of the bottom, which is that, all over x squared plus 2x plus 1 squared. That times nothing just is nothing, and so you get negative 2x, negative 2, and on the bottom, you get that. And there is a sneaky style point issue here. I'm going to take negative 2 out, not that that's a big deal, but that's not the problem. It's easy to forget where the bottom came from and to think that that's okay. That's the best that can be. But x squared plus 2x plus 1 squared can be written in an even nicer version of itself than that. Can anybody see?
X plus 1 squared. Squared?
Yeah. X plus 1 squared. Squared. But isn't that just x plus 1 to the 4? So it's not as weird as it looked. Agreed? And I didn't expect this, but I'm actually kind of happy. Vanessa, here is a situation where you can actually do a cancel. Can you see that there's an x plus 1 in the top and there's an x plus 1 to the 4 in the bottom, and the top is totally factored and x plus 1 is one of those factors?
You don't have to FOIL out the x plus 1 to the 4?
Oh God, no, that would not be a good move. I wouldn't want to do that. But what you can do is, can't you cancel the x plus 1? And have x plus 1 cubed left? That makes sense? And that's pretty rare, by the way. I wasn't even thinking of that when I made the question up. The fact that I got it to happen was just sheer coincidence. It's not a typical thing, right? It doesn't happen a lot, but I mean, it does happen. You see it happening here.